Hi there. So it's me again, Mr. Bailey. Today we're going to have a look at further work with variable acceleration. In particular, this lesson, how integration can help us to solve kinematics problems where the acceleration may or may not be constant. First of all, though, we've got 4 warm-up questions for you to try. So as usual, here they are. Have a go at them now on your own. When you're ready to see the solutions, play the video again and just double check using this video to make sure you're on the right lines and your solutions match mine. So let's start by having a look through question 1 together. For question 1, we've got a car travelling in a straight line at a constant speed of 45 kilometers per hour for 1 hour 20 minutes. So it says here to find the total distance travelled using the SDT triangle, the speed distance time triangle. So you may have seen this at GCSE. In fact, I imagine you will have done, either in maths, physics lessons or both. So here it is in case you can't remember it for some reason. So we've got S, D and T, and the way this works is you cover up the variable you want to find out. And so because we want to find the total distance, what we're going to do is we're going to blot out the distance, and whatever's left tells us what to do. So we're left with speed and time next to each other, S for speed, T for time. Because they're next to each other with no mathematical instruction, that means you multiply one by the other. In other words, D equals S times T. Distance is speed times time. So if the speed is 45 kilometers per hour, bear in mind the units of time in the speed are in hours. And so we need to make sure that we input the time in hours only, not hours and minutes. So what I'd suggest we do is we input it in terms of hours and minutes as a fraction. So 20 minutes is 20/60ths of an hour. You could have put 1 1/3 hours, or even 4/3 of an hour. So if you try this on your calculator, you should arrive at an answer of 60 kilometers. So I'm just going to show you using this ClassWiz emulator. So 45 multiplied, put brackets in, then type in, whoops, not that, shift mixed number, so 1 and 20 over 60, close bracket, press equals, and we do get 60 kilometers. And so that's our answer using the method part A. So from part A we get that it's 60 kilometers. For part B, we're asked to make use of the equations of Suvat, of which there's 5. And just to remind you, you do get these given to you in the examination for year 13. So here they are. These are in the formula book. It's great to know them, obviously, if you can, but just in case you don't or you forget them, they are given to you, which is always a bonus. So we can just think about what we know here in terms of the Suvat variables. So in terms of Suvat, what are we told? What do we know? Get rid of that little pop-up there. And so S, the displacement, that's what we want to know. So let's put a question mark by that because we are actually interested in this. U, as in V, is a constant. It's 45. The acceleration isn't changing. The acceleration is 0. And so U will be the same as V, which will be 45. The time we are told, the time is 1 hour 20, which again, in terms of hours, is 1 and 20/60ths of an hour. So in terms of what equations we can use, as long as it involves S, because we know U, V, A and T, it doesn't really matter. What I'm going to suggest we do is we go for this one here. S equals UT plus a half AT squared. And so using S equals UT plus half AT squared, because the acceleration is 0, the half AT squared bit just becomes nothing. So it's just a case of U multiplied by T. U is 45, and T, in terms of hours, just keep the units consistent with the units of speed, that's 1 hour and 20/60ths of an hour, which again, as in part A, that's going to give us 60 kilometers. For part C, using a velocity time graph, we need to remember with a velocity time graph that the area under the graph equates to the distance, or displacement rather, that an object or particle travels. And so let's sketch our axes out. And so we've got here time on the horizontal axis and v on the vertical axis. We can then add in our straight horizontal line of speed at 45 and put the upper bound of t where we're interested in it being, which is 1 hour 20, where this constant speed apparently or presumably ends. And then remember that the area under this graph equates to the distance travelled, which I've coloured here in yellow. So the area of this rectangular shape is obviously going to be the length of it times the width. The length is going to be, in terms of the time units, 1 hour 20, which in terms of hours, which is 1 20/60 of an hour. The height of a rectangle is 45 units of speed, 45 kilometers per hour. And that again gives us 60 kilometers, as you'd expect. That's question 1 completed. For question 2, we've got this particle moving from rest in a straight line in the positive x direction with a constant acceleration of 2. We're asked to find the displacement when time is free, first of all. So again, because it's constant acceleration, we can use the Suvat formulae. And so we're after the displacement, so let's put a question mark next to displacement. We want to know this. It moves from rest, and so the initial speed u is 0. We're not told the final speed v, nor are we asked to define the final speed. So we don't know it, nor do we care about it. And so we can just put a line through v, because we're not interested in it in any way, shape or form. The acceleration, however, is 2 meters per second, so we can input that in terms of something we know. And the time is when t is free. And so in terms of the Suvat formulae, we need the one which doesn't involve v at all, and we'll solve for s. And so again, what we can use for part A is the formula s equals ut plus half at squared. Because the particle starts from rest, u is 0, so ut is 0. So we're just left with half at squared, which is a half multiplied by the acceleration, which is 2, multiplied by the time, which is 3 squared. So a half multiplied by 2 multiplied by 3 squared, that's going to give us 9 meters. So for part A, we have a displacement of 9 meters. For part B, precisely the same idea, only now the variable time changes from being 3 to being 4. And so for part B, again we have s equals ut plus a half at squared. Ut, again, is 0 because initial speed is still 0. And we have half times 2 times 4 squared, and this gives us 16 meters. So after 3 seconds it's travelled 9 meters, after 4 seconds it's travelled 16 meters. It therefore stands to reason that between 4 seconds and 3 seconds it's travelled 16 take 9, which is 7 meters. That is to say that in the fourth second, yes, it's travelled 7 meters. And so we can add this in, and that's our answer for part C. 3 part A, we have a curve, y equals 6x minus 2x squared. And we're told this has a maximum at the point 3/2 and 9/2. And so using this, we need to show that it's got this maximum. So we can't just use this on blind faith, we need to prove it. So we've got this curve here, y equals 6x minus 2x squared. What we need to do first of all for part A is find the gradient function, dy by dx. So dy by dx, the 6x becomes 6. The minus 2x squared is going to become minus 4x. This 2 comes to the front and multiplies a coefficient of 2 before it. 2 times 2, as I say, gives us 4. The new power of x drops from 2 to just 1. And this gradient function is going to be 0 at any turning point. So that's going to be 0 at turning points. So because a maximum or a minimum is a turning point, we can set this equal to 0 now and solve for when this is equal to 0. It's not too hard to solve this equation at all. This is going to be equal to 0 when x is 3/2. So x is going to be 3/2 at the turning point. PT just means point. I'm just being lazy here. So anyway, we need to prove now that this isn't just any old turning point, maximum, minimum, or point of inflection. We need to show that it's in particular a maximum. And to show that it's a maximum, we take the second derivative. We differentiate the gradient function. So d squared y over dx squared. So we're differentiating this now. The 6 vanishes. The minus 4x just becomes minus 4. And it's not dependent on x. It's a constant minus 4, which obviously is less than 0. We need to remember, when the second derivative at a turning point is less than 0, that's proof that that particular turning point is a maximum. When the second derivative at a turning point is greater than 0, when it's positive, that shows that it's a minimum. So we've just shown now, using the second derivative, that when x is 3 over 2, we have a maximum. So we've shown that x being 3 over 2 yields a maximum, but we've not shown that the y-coordinate is 9 over 2. To show that y is 9 over 2, we just input x is 3 over 2. So when x equals 3 over 2, y is going to be 6 lots of 3 over 2 minus 2 lots of 3 over 2 squared. So if we try this on our class whizzes, so 6 lots of 3 over 2 minus 2 lots of 3 over 2 squared that does indeed give us 9 over 2. So therefore, we've shown that the point 3 over 2 and 9 over 2 must be a maximum point. My rubbish writing looks like it says maximum, but it means maximum. Apologies for my bad presentation skills. Anyway, going on to part B. I'm just going to do this in a different rectangle just so I'm not getting it confused with part A down here. So for part B, it says hence, that's a big clue, so we're going to use our answer to part A to help us. We need to show that this curve here has a maximum point at a different place. So what I'm going to do now is to think about y as f of x. So if we just write the initial function y as f of x and think about the input here. So what's happening here is whatever x is, y is 6 lots of it minus 2 lots of x squared. Whereas here, this function is pretty much exactly the same, but instead of x, x has just been swapped out, replaced with x plus 2. And so if f of x has an input of x, this function down here has an input of x plus 2. And so if this is f of x, we can say this new equation down here, that's f of x plus 2. So now we can try and remember about the transformations of graphs which we studied earlier in the year. So what we can say now is, if we define f of x as the original function, which is 6x minus 2x squared, then we can say that f of x plus 2, which would be this function here, 6 lots of x plus 2 minus 2 lots of x plus 2 squared. Now we just need to remember the basics of transformations of graphs. So to move from f of x to f of x plus 2, the change has only happened inside the brackets of f of whatever. And when the change happens inside the brackets, the change works in the opposite to common sense to what we'd expect. So rather than going plus 2 units, we actually move back 2 units. So rather than x being shifted 2 units to the right, the graph gets moved 2 units to the left. And so f of x plus 2 is a translation of f of x two units left. So every x coordinate just gets shifted 2 to the left. So therefore, the maximum of this curve here is going to be 2 to the left of what the maximum of this function here was. So the maximum of y equals 6 x plus 2 minus 2 lots of x plus 2 squared is going to be this here, but 2 units to the left in the x direction. So 3 over 2 minus 2, that's going to be at minus a half. The y coordinate isn't going to change. The y coordinate is still going to be 9 over 2. And so we need to spot this is actually a question going back to transforming graphs. Once we get that, it's not as hard to work out. And finally, from the warm-up, we have Calculus Corner, which has become a permanent fixture now. So we've got here that at time t seconds, where t is at least 0, a particle is moving along the positive x-axis and has displacement such that the displacement is equal to 3t minus 1.5t squared. Find the displacement when the particle comes instantaneously to rest. So the particle is going to be at rest when its velocity is equal to 0. So it's at rest when v is equal to 0. We need to remember though that the velocity is the instantaneous change in displacement with respect to time. So v is the same as ds over dt. That's how we can define velocity in terms of infinitesimals in a calculus manner. So we differentiate this function here, s, with respect to time, and we get 3t becoming 3, and 1.5t squared. If we differentiate t squared, we get 2t. So 1.5 multiplied by 2t is 3t, all minus. So 3 minus 3t equal to 0. So therefore this is going to be equal to 0, obviously, when t is equal to 1. So t is equal to 1, and the velocity is equal to 0. That was a bit strange, just change randomly to red. Never mind. So now we need to work out the displacement when t is 1. So when t is equal to 1, s is going to be equal to 3 lots of 1 minus 1.51 squared, which is at 1.5 meters. So after 1.5 meters of travel, the particle stops for a moment before then coming back towards the origin from where it left. Now we're going to move on to the main course of the lesson, as it were. So what we can do here, as ever of course, we can think about integration as being the reverse process of differentiation and applying this idea to calculus and kinematics. So if we start off by thinking of displacement, velocity and acceleration, then displacement normally has a letter s, and if we differentiate that, we get the velocity, which is ds by dt. We can then differentiate the velocity again, and we get the acceleration, which is dv by dt, which is the same as d squared s over dt squared. So the acceleration is when we differentiate the velocity, or when we differentiate the displacement function twice. Going in the opposite direction, starting with the acceleration, we can do the opposite and go backwards. Opposite of differentiating is integrating, and that tells us the velocity. So the velocity is the integral of acceleration with respect to time. Then going one step further, we can then integrate that as well to get back to the displacement, which is the integral of velocity with respect to time. So let's have a look at the falling object without having to rely on the Suvat formulae. So if we think about a stone now, being dropped from rest at t equals 0 from a height, let's just say it's x meters above the horizontal surface. So as the time t increases, the stone falls further and further until it eventually strikes the ground. By modelling the stone as a particle and using the constant g, which is 9.8 meters per second squared, we need to find in terms of t an expression for velocity v in terms of t. So what we need to remind ourselves here of is what g actually represents. And so g, by its definition actually, g is the acceleration due to gravity. The key word there being acceleration. So we can use this for our solution to part A. So using what we just saw on the previous display, the velocity is the integral of acceleration with respect to time. But this acceleration is going to be the acceleration due to gravity. So A is going to be g, which is this constant 9.8. So the integral of 9.8 with respect to t. If we integrate a constant, we're just going to get that constant multiplied by the variable with which we're integrating with respect to. So that's going to give us 9.8t plus the constant of integration. However, the stone's dropped. It's not thrown down, it's not thrown up. So because the stone is dropped, we can infer from that that the initial speed when t is 0 is 0. So when time is 0, v is equal to 0. We can now substitute these initial conditions into the expression we've obtained for the velocity of this object. So we just substitute in now that v is 0 when the time is 0. So 0 equals 9.8 multiplied by 0 plus the constant of integration. Therefore, obviously, the constant of integration must be equal to 0. And so we have that the velocity of the particle is just simply given by 9.8 t. For part B, we now need to be thinking about an expression for the displacement, vertical displacement of the particle s in terms of t. And so using integration only, s is going to be equal to the integral of velocity with respect to time. And the velocity we now know as a function of time is 9.8 t. So that's 9.8 t dt. And so the power of t, as we know now, increases by 1, and the new power divides the original expression. And so we get 9.8 t squared divided by 2. 9.8 divided by 2, that gives us 4.9 t squared, and then again plus c. But again, the initial conditions are that when the time is 0, there's been no displacement because it's just been dropped. And so the initial displacement is 0. So if you substitute these in to work out what the constant of integration is, we'll see again that this constant of integration is going to be equal to 0. So s is 0 when the time is 0. So 4.90 squared plus c equals 0. So therefore, once again, the constant of integration is 0. And we then have that the displacement is given by 4.9 t squared. And so we've derived two expressions by using integration. Let's just compare this for a moment with Suvat. We were told not to use Suvat, but it's now worth showing you that if we did use Suvat, we would get something which is consistent with these results. So the acceleration of this object falling is g, which is 9.8, which is a constant near the Earth's surface of 9.8. So we could have used SUVAT. So if we did use SUVAT, and we used SUVAT to solve for part A, for velocity, here's what we would have got. So we want to work out the velocity. So we'd put here, that's a question mark, because we want to find that. U is equal to 0. A is 9.8. S, we don't really want to know, we're not particularly interested in S. And the time, let's just say time equals t. We want the function of time in here somewhere. I'm not interested in S, so we'll leave S out of things. And so what expression could we use for V, which doesn't include S? We could have used V equals U plus AT. So U is 0, A is 9.8, and T we just leave in as a variable. So again, we would have got V equals 9.8T. For part B, trying to find S as a function of these variables. So we want S as a function of T. We could have used S equals UT plus half AT squared. Again, like I've mentioned before, the initial velocity U is 0, so this makes UT equal to 0. So we would have got half multiplied by A, which is 9.8. Half times 9.8 is 4.9. Then we just have T squared, which is exactly what we achieved using integration. So it does prove that integration gives you the results you'd expect. Let's have a look at a worked example now, where we're going to solve some problems using integration. So we've got here that a particle is moving on the x-axis. At time 0, the particle is at the point where x equals 5. And so we're told here that the initial displacement is actually 5. It's not starting with a displacement of 0. So just pay attention to that. The velocity of a particle at time t seconds, where t is at least 0, is 6t minus t squared meters per second. First of all, we need to find an expression for the displacement of the particle from 0 at time t seconds. So we need to remember now that we need to be integrating to find the displacement. But first of all, let's just relate velocity to the variables x and t. So this particle's moving along the x-axis. Okay, so we can say that the velocity is the instantaneous change in displacement as a function of time. So the displacement, because it's moving along the x-axis, instead of just being generally ds by dt, this will be dx by dt, because it's moving along the x-axis. So what we need to do here to find the displacement, which is going to be x, you're going to have to integrate with respect to, so we're going to have to integrate the velocity with respect to time. So we are told what the velocity is. The velocity is given by this expression here. So if we integrate that, 6t minus t squared with respect to time, what we're going to get, 6t is going to become 6t squared over 2, which is going to be 3t squared. T squared is going to become 1/3 t cubed, so it's going to be minus 1/3 t cubed. And then, as ever, when we integrate, we need to consider this constant of integration, which I'm going to call, again, big C. We now need some initial conditions to decipher what this constant of integration is. Now, we are told here that at time t equals 0, the particle is at the point where x equals 5. So we can now substitute in, when t is 0, x is equal to 5. So if we just put in now x is 5, So 5 equals 3 lots of t squared, so 3 lots of 0 squared, minus a third multiplied by t cubed, which is going to be 0 cubed, plus c. We can now see that c must be equal to 5. And therefore, the displacement x must be 3t squared minus a third t cubed plus 5. And we've solved that for part A. Now let's think about part B. So let's just give myself a bit more space here for part B. So we need to work out the distance of a particle from its starting point when t is equal to 6. So for part B, when t is equal to 6, let's see what we know. Well, the displacement is going to be 3 lots of t squared, so 3 lots of 6 squared, minus 1/3 6 cubed plus 5. If you try this on your class whiz, you should be getting that that's 41 meters. But we're not after the displacement as such, we're after the distance it's travelled from its starting point to when t is 6. So we need to be careful here. This is almost, I hate this phrase normally, it's almost a trick question, because actually it starts at x being 5. So a big but. The particle started where x is equal to 5. So therefore, the distance from the starting point is going to be 41 minus 5. So actually the distance travelled is 36 meters. That's another illustration of how you need to be very careful if you're talking about the distance travelled or displacement. They are two definitely distinct concepts. Let's have a look at another worked example. And so this time we've got a particle travelling once again in a straight line. After time t seconds, we've got this expression for its velocity. So we need to find the distance travelled by the particle in the 3rd second of its motion. Again, big point here, we're asked for the distance travelled, we're not asked for the displacement, so just let's take some care. So we can start by finding the displacement, because displacement relates to the velocity. So once we get the displacement, we're going to need to interpret this in the right way to work out and deduce what the distance is. Not necessarily the same thing as the displacement, sometimes is, sometimes isn't. So anyway, what we need to remember here is that the displacement, like we mentioned before, that's going to be the integral of velocity with respect to time. Now, we want to find this displacement, well, distance rather, in the 3rd second only. And so the 3rd second begins when the 2nd second ends, so we're going to start this interval from the end of the 2nd second, and we're going to stop considering the distance travelled once it gets to 3 seconds exactly. After 3 seconds, it goes to 3.01 and enters into the 4th second. And so, in particular, this is the integral in between 2 seconds and 3 seconds. So, velocity, we've got this expression for it, which we can use. The velocity is 5 minus 3t squared. So if we integrate this, big squared brackets now, 5 becomes 5t, t squared becomes t cubed divided by 3. And so 3t squared is going to become 3t cubed, all divided by 3. The 3's will cancel, so we'll just have t cubed. But of course this is a minus, so we're going to get minus t cubed. And this is going to be in between the limits of 3 and 2. And so we do the higher limit first. And so we're going to input when t is equal to 3. So we have 5 lots of 3 minus 3 cubed. We're going to subtract away what we get when we input the lower limit. So when t is 2, that's going to give us 5 lots of 2 minus 2 cubed. So if we just use the calculator, or otherwise if you're confident, but I'd always suggest use your calculator to be honest here. So this first one here, 5 times 3 minus 3 to the power 3, that gives us minus 12. We're going to minus off this next bit here, which is 5 times 2, 5 times 2 minus 2 cubed, which gives us 2. So we're going to have minus 12 minus 2, which weirdly gives us minus 14 meters. So the displacement is minus 14 meters, which is strange. So we need to think about why we're getting a minus here. So what we could always do with doing, to be honest, is doing a sketch of the diagram. We need to remember when we integrate, we're in danger of getting a negative answer if the function falls below the x-axis, or in this case the t-axis. So let's have a look at a sketch of what we would have got. This is a sketch of v against t for this function here. So if I just highlight the function, just to show what we're actually graphing. So obviously it's minus 3t squared, so it's going to have a characteristic negative unhappy parabola shape, so it's going to fall below the t-axis at some point. It ends up falling below before t is 2. We can actually work out the t-axis intercept, and so it's going to be equal to 0 when 5 minus 3t squared is equal to 0. So 5 minus 3t squared is equal to 0. So we have that 3t squared equals 5. Therefore, at this point here, t must be 5 over 3 square rooted. Let's see what that gives us. It just helps to form a picture for us of what's going on. Oops, don't need that bracket actually. So that's 1.29-ish seconds. We need to be careful, you see, if this function is a bit above and a bit below the t-axis. If it was a bit here and a bit there, we'd need to change our limits to work out the bit above first, and then the bit below separately. But because we've now seen that this is all below the x-axis, we can keep this okay. We can keep this as it is, and just realise here that the area of this bit would be 14. So although the displacement is minus 14, the distance travelled is positive 14. So using this sketch to help us, and this information here, we can therefore deduce that the distance travelled must be 14. Distance, underlined in bold, to make it clear we're not talking about displacement, distance travelled is 14 meters in that third second. Finally, I just want to show you this worked example, which was actually from an old past paper question. It also involves integrating with respect to E, which we've not covered yet. This is a glance ahead to year 13, but the concept here is fairly intuitive, being the opposite of differentiation. So I'm just going to drop this in for you and mention it before we get to part C. Anyway, for part A, we've got that this particle's moving in a straight line. We have this function of v, and we need to find an expression for the acceleration of the particle at time t. So we just need to recall here that the acceleration is dv by dt. It's a rate of change of velocity with respect to time. So for A part 1, We just need to remember the initial concepts in terms of derivatives that relate v and a. And so a is dv by dt. So if we differentiate each term piecemeal, so 6t squared, if we differentiate this, it becomes 12t. If we differentiate this function here, what's going to happen is this minus 4, the function of t in the power, is going to drop to the front and multiply this minus 2 in front of it. The actual power of e, as you should know by now, never actually changes, it stays fixed. Because when you differentiate any power of e, the power of e stays the same. That was in chapter 14, exponentials and logs. So anyway, if we differentiate this, the coefficient becomes minus 2 multiplied by this minus 4 in the power, which gives us positive 8. And as I say, the power of e stays as it is. So we have e to the power minus 4t. We then need to differentiate this constant 8. If you differentiate a constant, it disappears. And so we've got it here for part A. So this is the expression for the acceleration for part 1. We next need to work out for part 2. So part 2, we need to find the acceleration of a particle when t is in particular 0.5. So we're just going to substitute in that t is 0.5. So when t equals 0.5, A is going to be 12 lots of 0.5 plus 8 lots of e to the power minus 4 times 0.5. Well, 4 times 0.5 is going to be minus 2. And so we can just evaluate this, but we do need a calculator. Unless you can do powers of e in your head, which I very much doubt. So 12 multiplied by 0.5, then plus 8 lots of e. Now to get e, we press alpha and then this power button here, x 10x, this standard form button. Then we do that to the power of minus 2, press equals, we get this decimal. Read the question, it does say we need to give this to, have I just made that up in my own head? I think I have. Sorry, what am I talking about? Talking absolute nonsense. Anyway, what we should do by now, what we should know, is that if in doubt, give answers to 3 sig figs. And so I'm going to give this to 3 significant figures, so call that 7.08. Pop the units in. It's going to be meters per second minus 2. Sorry, meters second minus 2. So that's part A completed. We can now think about part B. For part B, we're told that the particle has a mass 4 kilograms, 5 magnitude of a force acting on the particle when t is 0.5. Well, this should remind you very quickly of what's the relationship that links together force, acceleration, and mass. That's Newton's second law. We're going to use force equals mass times acceleration here. So for part B, force is mass times acceleration. So we're told what the mass is. The mass is 4. It's going to multiply that by the acceleration of the particle, which we worked out here. 7.0 blah blah blah, whatever it was. To avoid any rounding error, let's just store this value in the calculator and just multiply it by the mass, which is 4. That gives us 28.3 newtons to 3 significant figures. We now come to part C. When t equals 0, the particle is at the origin. Find an expression for the displacement of the particle. So for part C, we need to remember that S is going to be the integral of v with respect to time. So you need to integrate this function here with respect to time. But how on earth do we integrate a a power of e. So I'm just going to remind us of what we saw in chapter 14. So from chapter 14, what we saw is that we have a function of x, which is e to the power ax plus b. But if we differentiate this, the a multiplies the power, sorry, a multiplies e to the power of whatever. So intuitively, if we just remember that integration is the reverse process, the opposite of differentiation, then hopefully we can intuitively see that when we integrate, instead of this a multiplying, this a is actually going to divide. And so if we integrate e to the ax plus b, what we're going to get here is 1 over a multiplied by e to the ax plus b. In other words, e to the ax plus b is divided by the a when we integrate versus being multiplied by the a when we differentiate. And obviously we have this constant of integration to consider. So we can use this now for part C. So we need to integrate v with respect to t. So let's have a go at this. So we're going to be integrating make a link to show that this is carrying on from above. So we're going to integrate 6t squared minus 2e to the minus 4t plus 8 with respect to time. And so this 6t squared is going to become 2t cubed. This minus 2, like I mentioned here, is going to be divided by this minus 4. Minus 2 divided by minus 4 is going to be positive a half. So we're going to plus a half e to the minus 4t. This constant 8 is just going to become 8t. And then we're going to have this constant of integration to consider. So we now have these initial conditions. We're told when t is 0 for particles at the origin. So we can input now that when t is equal to 0, s is equal to 0. So therefore s, which is this expression here, 2t to the 0, sorry, 0 cubed I mean, that's obviously going to be 0, then plus half e to the 0. If t is 0, this is going to become e to the 0, then plus 8 to the power 0 plus c. And so you can hopefully see here that all these terms are going to be equal to 0. However, e to the power 0, anything to the power 0 is going to give us 1. So half times 1, that's going to give us half plus c. So therefore, actually, c is going to be equal to minus a half. So the expression for the displacement is now actually going to be s equals 2t cubed plus a half e to the minus 4t plus 8t minus a half. And so we've actually finished off this question here, and also giving you a glimpse at how you integrate the functions of e. So now, as ever, it's over to you. So if you can try and have a look, please, at 11D on page 189 of the Stats and Mechanics Year 12 book. Try all the questions in that book on the exercise. Use the answers in the back to self-assess. If you get stuck, just try and ask me, send me an email, leave me a comment in the comment section. I will get back to you. So please don't suffer in silence. Please don't shy away from doing your best. So try those, as I say. Be in touch with proof of your work if you can, and you'll hear from me again either in the next email or the next video. Thanks for listening. I'll speak soon.